thanks to all of you for coming out to hear about the machinery of big data science on this nice, fine fall day. I also want to thank, of course, Tim's co-convener for the series, Fred Adams, for inviting me to speak today. And before I go into my topic, I do want to give you a little bit more about who I am. As was already said, I am a research scientist. I'm interested in dark matter, and I'm also interested in creating new capabilities to do large-scale science. If any of you were here 22 years ago when we started Saturday Morning Physics, I gave one of the 2 inaugural lectures 22 years ago this December on the dark matter puzzle, looking for 90% of our universe. A little bit about big data, since it's in my title. There are 2 definitions that I put on this slide. One is from NIST. They set standards. And in their point of view, big data consists of extensive data sets that have some interesting characteristics: volume, velocity, and variety, and that require a scalable architecture for efficient storage, manipulation, and analysis. Perhaps a more simple definition is big data is used to describe any time you have a massive amount of data that you can't deal with in traditional methods using either databases or software. Of course, I'm sure our president would have some suggestions about how we could improve the situation. So, since I'm going to be talking about the size of data quite a bit, I wanted to make sure that everyone was aware of what the terminology is. And so CERN actually has a very nice video that describes the various data sizes using a DVD as an example. So I'm going to show you that. So you have a DVD, and 1 byte of data is 8 bits, and that gets encoded on a track on a DVD, a set of zeros and ones to create each character. If you take 1,024 of those, that would represent about 1 page of data. And so you could imagine encoding that on a DVD, and that takes up about 3.2 millimeters along in the linear distance on a DVD. If you were to increase by another factor of 1,024, taking all of those pages and maybe making a book, you'd end up with a megabyte. And if you put a megabyte on a DVD, you end up with about 9 tracks going around the DVD. So to take the next jump in scale, we could take 1,024 of those megabytes, producing a gigabyte. That's about a quarter of a DVD. And that could be something like a high-definition movie. Taking the next jump, going to a terabyte, that's 1,024 gigabytes. That's a stack of 240 DVDs. If you then take the next jump by another factor of 1,024, you end up with a petabyte. And that's a stack of DVDs that's roughly equivalent to the Eiffel Tower. Now, for the scale of data that we deal with at the LHC, we're talking about around 100 petabytes a year. And that's 4 stacks of DVDs the size of Mount Everest. That's a lot of data. This is another way of representing that. The stair steps increase by a factor of 1,024. And in the boxes, we have the different nomenclature, starting from kilobyte, megabyte, gigabyte, terabyte, petabyte. Beyond petabytes, we have exabytes. That's 1,024 petabytes. Beyond exabytes, we have zettabytes. That's 1,024 exabytes. Or if you actually take another step, you have a yottabyte. And a yottabyte is a very long number of bytes. There's actually further places to go beyond that, but I don't know of any conventional use for these terms yet. That's why actually you see multiple possible names when you get up to 2 to the 90th or 2 to the 100th bytes. Little cartoon about big data. So, some fun facts about big data. There's approximately 3 zettabytes of data in the digital world today. That number might vary. Maybe it's 2, maybe it's 5. These are all estimates. But if you use 3 zettabytes, that's data equivalent to every person in the United States producing 3 tweets every minute, 24 hours a day for almost 50,000 years. Another way to look at this is it represents about 824 billion high-definition movies. If you were to watch those, it would take you 188 million years. Walmart handles more than 1 million customer transactions every hour, and they actually have databases that are on the scale of 2.5 petabytes. Interestingly, all this data is out there. An MIT study estimated that only about 0.5% of that data is actually analyzed and used effectively. The cartoon on the right shows this. You see somebody looking at a monitor that says database of useful information, 5 kilobytes. Database of useless information, 500 million gigabytes. Some more fun facts. We're performing about 63,000 searches on Google alone. That's about 2 trillion searches per year. Interestingly, Google reports that 16 to 20% of the queries that they get have never been asked before, every day. A single Google query actually gets fanned out to about 1,000 computers to answer your one question to Google. And every one of those queries has to travel an average of about 1,500 miles to get back to you, to and from Google back to you. So the cartoon shows a common problem. Here's a list of 100,000 warehouses full of data. I'd like to have you condense this down to one warehouse that has all the useful data. And that's part of the problem with big data. Where do we look to extract useful information from that data? Of course, a lot of the data that I was just talking about is commercial, it's user behavior, it's all sorts of things, but science has this same problem with big data challenges. And so this is due to a number of different reasons. Technology is, of course, advancing. The way we do science is advancing with it. We have increasingly complex sensors that produce a lot more data, very complex data. There's lots more data sources. You've heard of the Internet of Things. Your toaster may be online. Your refrigerator may be online. They estimate that by 2020, every person in the US will have an average of 12.5 devices, each with their own address. There's evolving scientific instruments. We have more detectors in our instruments. The detectors have more channels. There's more complex information coming from those detectors. And correspondingly, the cyber infrastructure that we're using to handle all that data is also getting bigger. And we produce data from data. So there's a lot of reasons that we have this flood of data that we have to deal with. And what we really need is an appropriate machine to help scientists address this challenge. And in honor of Halloween, I had to put that cartoon in. So what's the problem? So we have all of this data, and it has a number of characteristics. There's volume, variety, and velocity. And it's very difficult for researchers to actually deal with this data and extract scientific meaning from it. For example, scientists usually want to focus on their science. They're not data experts. But often they have to become data experts to actually use the information that they're gathering. Applications that have to deal with this data typically work well at the scale of your laptop or desktop computer, anywhere from tens of gigabytes up to terabyte scales. When you go beyond that, though, things start to fail badly. It becomes a real challenge to be able to look at that data, to be able to understand what it's telling you, and use the information to get scientific insight. Data velocity can mean that the data you're looking at is remote. You're going to need ways to get access to that data, to bring it someplace where you can look at it. And often, this data is changing almost in real time in some situations. And that makes it very difficult to exploit the data. The data volume often requires that the data has to be stored in multiple locations. Certainly, you can't fit it on your computer. Maybe you can't fit it on your local cluster. Maybe your institution doesn't even have enough space when we're talking about these huge volumes of data. So you're going to have to use networks, distributed systems, all tied together to host this data and make it accessible for you. And so this, in a big picture, is sort of the reasons we have challenges with big data. Scientists really need tools, applications, infrastructure that really make it easy for them to pursue their science. So ideally, they'd get some big data machine that would hide all the complexity, all the interesting, intricate knowledge that they would have to have so that they can focus on their science. We're going to explore what that might look like in a little bit, but first, because I'm a high-energy physicist, I want to use my own regime as an example. So in high-energy physics, we've had big data challenges for a long time. So certainly for the last 40 years, we've had challenges in bringing groups of physicists together to do high-energy physics experiments. These experiments have gotten increasingly complex, larger scale, and it requires more physicists to come together, to work together, to actually deliver the experiments, all the detectors, and all the infrastructure to carry out these experiments. And currently in high-energy physics, we really have global collaborations typically, because that's what it takes to get the funding, expertise, knowledge, capability all put together to do the science. Collaboration was really a key for us, being able to work together effectively to do everything that needed to be done, and to be able to look at all of the information that we're getting, understand it thoroughly, and be able to extract new scientific results from that information. I mentioned high-energy physics. I assume most of you are at least passingly familiar with it, also called particle physics often. High-energy physics is about exploring the forces and fundamental constituents of nature by colliding high-energy particles and reconstructing them. Think about slamming two cars together to find carburetors and engine blocks and batteries to see what they're made of. It's similar with what we do in high-energy physics. So these particle collisions really shed light on the fundamental nature and structure of matter. For high-energy physics, the most important scientific instrument is the LHC, the Large Hadron Collider. That's located in Geneva, Switzerland. And ATLAS is one of the two primary colliding beam experiments at the LHC. I'm a member of ATLAS. And we're trying to address fundamental questions about our universe and its composition and structure. So on the left here, we have a bird's eye view, an aerial view of the area around CERN. It spans Switzerland and France, just outside of Geneva. The first run started in fall of 2009. We're now in what's called Run 2, which started in 2015 and will run for about another year. It ends in late November 2018. On the right is a diagram of the ring that's underground, where we have these protons traveling, two beams traveling in opposite directions. And they collide at a couple locations around the ring where we put big detectors. ATLAS is close to what is in what's called point 1. It's a general purpose experiment looking at all sorts of physics. And CMS is our competitor for both general purpose and large. Think of these experiments as very big three-dimensional cameras that can take pictures 40 million times a second in high resolution. Grid computing. This is really high-energy physics big data processing machine. It's working toward that vision that I mentioned of having something in place that hides all the complexity and lets you pursue your physics goals. So some of you may have heard of the grid. That's an implementation of distributed computing. We have need for so much computing, we can't locate it at any one location on Earth, right? We have to take advantage of computers and storage all over the world. And so we've relied on something called the grid, which was conceived in the late 90s as a way of providing a distributed computing model that would let us access and use all of those resources. It's analogous to the power grid in some sense. You know, the concept would be just like you plug in something into the wall and you magically have electrical power. You'd like to be able to just sort of plug into the grid and have computing power to be able to look at your data. This was our plan A. We didn't have a plan B. Fortunately, it did work, and it's actually working pretty well. And the grid really allows all of these distributed resource owners to decide how they're going to share their computers and storage with experiments like ATLAS, CMS, and others. And it's been a very effective way to do that. Just as a little aside here, you can imagine that I said there wasn't a place big enough to put all the computing. It's not entirely true. One of the real reasons is funding, right? It's easier to get a national funding agency to give you money to build something in your own country. If you go to them and say, instead, I want you to write a check to CERN, and they're going to go buy a bunch of computers on your behalf and put them at CERN. It just doesn't go over as well. In addition, universities, like the University of Michigan, contribute significantly when they end up hosting and getting the credit for providing resources for this. So it's really partly a political and funding issue that the grid has evolved and continues to be important and relevant. Most of you probably heard about the Higgs boson. We actually made an announcement of a new Higgs-like boson on July 4th in 2012. We all suspected it was the Higgs boson. It took another 9 months to actually confirm that it was a Higgs boson by studying it. This made very big news all over the world. 1 billion people watched the event at CERN when the Higgs boson was announced jointly by Atlas and CMS. There was another interesting first. The CERN Director General actually pointed out the LHC computing grid as a critical part of the discovery. So this is sort of the first time that computing infrastructure was viewed as critical to a discovery and was suitably recognized. So I've talked a bit about science, big data, Atlas high energy physics collaboration. It's interesting to understand how we actually get the data from those collisions and process it, filter it, process it, and get it out to physicists all over the world. Fortunately, CERN has another nice set of videos that illustrate the process at a high level that I'll show you here. So remember the ring that I pointed to before. This is the ring. You can see bunches of particles moving around that ring, these little blobs. This is the Atlas detector about 100 meters underground. That's the size of a 7-story building. It's about 60 yards long. And you can see these little blobs of particles coming in and colliding. On the upper right, there's a timer going. That's in nanoseconds. Every 25 nanoseconds, particle bunches cross and produce collisions. So while that signal's propagating out, the next one's coming in. We have to quickly look through this data with electronics to decide, is this interesting or not? Most events are not. Occasionally, like you just saw, one of them gets through as interesting. This is the so-called level 1 trigger. So we're speeding up the clock now. You can see more things coming in, a few getting out. Next, we go to what's called the level 2 trigger. This is a set of computers, roughly 100 to 1,000, depends on which experiment you're talking about, that look at the data in much more detail. Each one of those computers is analyzing an event, making a decision, and saying, throw it away or send it on. So this is another level of filtering and selecting to get the right data. From here, the data is sent out through optical cables. That's Atlas, and you see the other 3 experiments as well, sending data to the so-called Tier 0 at CERN. This is the central computing center where data flows in from all 4 experiments and then is looked at by the Tier 0 computers. So what's important here is that all of these experiments have their own data formats, and they all need to be processed. And you can see the data coming into the data center. We have a huge number of computers there that try to very accurately reconstruct that electronic information to decide what the physics content is. And schematically, these are physics events of varying complexity that are being reconstructed. And it'll be shown here. Initial reconstruction of the event. This is an event with some level of detail. We make a copy of that data, and we send that copy onto tape at CERN. So the Tier 0 is actually responsible for making a tape copy of all of the raw data that comes off all the experiments. So these computers, in addition to reconstructing it, are making a copy and sending it off to these very large tape robots. And so we're going to zoom in here on some of the tape robots just to see conceptually data is moving in. And then there are these set of tape robots with tape heads that are taking the data, putting them on tape for long-term storage. And again, all of the data that comes out of all of the experiments at CERN is put on tape and stored there indefinitely. Another important thing that happens at the Tier 0 is that the initially reconstructed data and the raw data is sent off to the rest of the world. You'll see it here. The data flow in, the reconstruction, copy to tape, and then at the top, you see copy all the raw and reconstructed data off to that worldwide computing grid that I mentioned earlier. So we're sort of hinting at some of the pieces of the machinery. We've seen the process of how we get Atlas data out of these proton collisions and then sent out to the worldwide LHC computing grid, the WLCG. The important components that are involved in actually being able to look at this data are computers that are required to analyze, filter, and transform all of this data, storage to hold all of that data, and networks that actually tie those distributed computing centers with the storage and computers all together around the world. So they give us the ability to access, share, and distribute the data. So the worldwide LHC computing grid is pretty much running all of the time. As of September 2016, we had 63 sites around the world that had signed MOUs, Memoranda of Understanding. They've committed to providing resources to the WLCG. There are over 167 sites in 42 countries that are part of the WLCG. The picture on the right is sort of a snapshot of data moving between sites, the green lines that span the globe. I took this snapshot, I think, August 8th, right around noon. And in the upper right, you can see there are 340,000 jobs running. There's almost 500,000 CPU cores involved and a transfer rate of about 30 gigabytes per second globally, just at that point in time. The upper left is sort of a conceptual model where you have CERN at the center, a set of so-called Tier 1 centers, which I'll explain in a little bit. They're national scale centers. And then on the outer ring, a set of Tier 2 sites. There's about 140. In terms of the capacity of the WLCG, there's about 3.8 million HEPSPEC-06. That's just a benchmarking number that we use. It roughly corresponds, if you took today's fastest computers, that would be about 350,000 computers. However, we don't have the luxury of having all the newest stuff. We bought things over time. Some computers are 7 years old. So there's actually probably closer to 1 million cores available. Just some of them are much, much slower than the newer stuff. We have about 310 petabytes of disk. And we have tape systems that are currently storing about 390 petabytes. Networking, I mentioned it before, it's really critical because of the distributed nature of our work. In fact, we wouldn't have large scientific collaborations without having really ubiquitous, high-performing networks in between them. We really have, in high-energy physics, have pioneered enabling and exploiting networks for us because we have a lot of challenges. We have thousands of physicists that are all over the globe. We have tens of petabytes to even hundreds of petabytes a year of data that we have to deal with. And we have significant needs for computing and storage to support all of this work. A little bit about internet history I should bring to your attention. The University of Michigan actually played a critical role in development of what we currently have as the internet. There was a meeting that was held in 1987 where a number of people came to discuss the creation of a research and education network called NSFNet. And that has actually evolved into what we currently see as the internet. Another point is that a few years later, in 1989, working at CERN, trying to figure out how to share information and provide access to documentation and knowledge, Tim Berners-Lee sort of invented the World Wide Web. And point here is that physicists have been really integrally involved with networking scientific networking since its inception and continue to be so. This is a snapshot of some of the global research and education networks that provide high capacity links all around the world. Most of those lines that you can barely see are 100 gig connections that run between lots of locations. That's 100 gigabits a second. That's 100 times 10 to the 9th bytes per second being potentially transferred on each of those links. Here's a blow up of just the situation in the United States. If you look carefully near Michigan, you'll see a little link called Mylar, Michigan Lambda Rail, that leads off here to Ann Arbor. We have a 100 gig link. We participate in this global RNE network infrastructure that's supporting science globally. Atlas has a data distribution model starting from Atlas, which you saw in the video. We have data flowing out. In principle, if we didn't have to put all those little filters and checks, we would take 1 petabyte of data every second. We have no system that can handle data at that range. So that system that you saw that makes all those selections actually takes that petabyte a second and trims it down to somewhere between 200 to 800 megabytes a second. So a very significant reduction. Presumably the interesting data that we all want to look at. It then flows out to various national scale tier 1 centers and then on to tier 2 centers and all the way down to tier 3 centers and people's laptops. The computing model that we've developed is originally hierarchical. We have the tier 0 at CERN. And as I mentioned, one of its main responsibilities is to get everything onto tape. The concept is that there are then tier 1 centers, national scale centers, that also participate. They take the data, they fan it out, they manage sort of national scale clouds. And then there are approximately 100 tier 2 centers. These are regional centers. And in fact, I'm the director of the Atlas Great Lakes Tier 2, which is located here and at Michigan State University. We roughly split the resources and provide what looks like one center distributed across our 2 sites. And the idea here is that physicists who want to analyze the data, want to look at things, actually send their job into a system that tries to move their computing application to where the data is. So we have this large-scale central workflow management system in Atlas called Panda. And it manages all of those jobs. It manages all of these global resources and the data. And so it sort of match makes. It says, you have to run a job. Your data is here or here or here. These 2 are busy. I'll send the job here. And then the user's job gets there, does its processing, and the user, as part of the job definition, says, OK, the data should go back here. The user is then notified as soon as the job completes, and they can go get their data and do further work with that data. So the goal is really a production and analysis system that's as seamless as possible, and that gives us access to all of these resources transparently. So I would say, as an aside here, that we're not quite there, but that is certainly the vision and the goal. There's still a lot of complexity that, in many cases, gets exposed to the users that perhaps shouldn't be. The tiered centers vary significantly in their capacity. I've mentioned the tier 0 at CERN, the tier 1 scale, the tier 2 scale. One thing to notice here is that there's an awful lot of computing cores, computers, involved in doing this work. So I wanted to take a quick survey of the audience. How many of you either own a computer or work on a computer typically? That's what I expected. Keep your hands up. I'm going to ask you another question. How many of you have never had a problem with a computer? That's also what I thought. I'm sure it was the same in the room next door. So you can imagine that running this kind of infrastructure, in principle, is easy. In practice, there are a lot of difficulties in actually making this work well. So can we just take what we've developed within Atlas, within LHC, and say we've solved the big data problems? Well, not exactly. It's taken a lot of work to actually get to where we are, and a lot of the work is very specific to the kinds of things that we need to do in hydrogen physics. So it's taken hundreds of man-years to develop the software and computing infrastructure that we've developed, and it requires significant expertise and manpower to keep it going. So perhaps rather than trying to address the whole infrastructure and make it generic for everything, we should focus on enabling collaboration on big data, because that seems to be one of the primary challenges, especially if you have sets of scientists at different institutions that want to work together on the same big problems. That can be really hard. Big data sort of gets in the way. So I'm going to talk about this a little bit later when I get back to some of the research that's going on. So we've seen hydrogen physics as an example, right? We've given rise to this global machine that we're trying to make address our needs, ultimately gain new insight from this data and make new discoveries. And while hydrogen physics has been certainly a leader, a groundbreaker in this area, the future has many other science domains that are going to match or surpass the scale of data that we're doing in hydrogen physics. First, I'll talk a little bit about ocean modeling. I think most of you would probably agree that understanding the Earth's oceans is critical. They cover 70% of our planet. Without the oceans, we may not have any life on this planet. Imagine that you change the present ocean. That could result in a significantly different atmosphere. The ocean has more than 1,000 times the carbon compared to the atmosphere, as well as being critical in all sorts of carbon, nitrogen, oxygen cycles that populate the atmosphere. Changes to the ocean can give us a very dramatically different climate. And of course, there's also the issue of sea level, especially if you live in low-lying areas. So ocean modeling is very important. Current high-resolution models, three-dimensional models of the ocean, are on the scale typically of hundreds of terabytes of data. Next-generation versions of these ocean models that have all sorts of details, are finer-grained, produce a petabyte or more of data. To get 1 year worth of 3D information about the ocean, you have sort of a petabyte scale data set to use. And of course, that data is very interesting to oceanographers, climatologists. Lots of people want to have access to this, want to look at their own piece of that, and gather their own unique insights from that. So we need ways that we can share this data and allow researchers to effectively use it and analyze it. Again, it's the big data problem. Here's one example. This is a model that was run showing the vorticity in the ocean. This is the model data, by the way. And you can see these little eddies showing up, these little vortices. What's very interesting is if you take pictures from satellite and you do color filters that track plankton, you can see very similar features in the ocean. This model is actually very representative of what people actually see when they end up looking at the data of the real ocean. So there's lots of things going on in there. You can imagine studying all sorts of things in this model to try and gain better insight into how things evolve and change. Another model. Here's an ocean internal wave field. That's Africa and Australia shown there. And again, there are all sorts of things going on in here. The resolution isn't quite good enough to see all of the little nuances and details, but this is just the model running forward, and you can see the behavior in this part of the Indian Ocean between Africa and Australia. And there's a lot of detail in here, and there's a lot of different ways that you can look at this data. This is just the internal wave field. You could be looking at currents. You could be looking at currents in both directions. You could be looking at salinity, temperature. There's all sorts of data that's stored in these models and all sorts of ways that you can look at it. These two movies are just examples of showing you what kind of resolution and capability they have currently for modeling the oceans. So these ocean modelers need continued improvements in interoperable storage, computing, networking to allow them to continue to create these models and match them to what they observe. The machinery requirements that they need are actually very similar in many ways to what we use in high energy physics, right? It's having computers, it's having storage, it's tying it all together, it's making it accessible, making it usable. The level of detail that these ocean models are getting to is starting to get to the point where these are almost indistinguishable from real observations. So they have what's called a Turing test for their ocean models. Could you sit an oceanographer in front of a movie of observations and simulated data, and could he tell the difference? And they're getting to the point where they're starting to get accurate enough with these high-resolution models that that's very hard to do. And these models take, I think I mentioned it on a previous slide, something like 30,000 to 100,000 CPU cores working for weeks to generate these models in detail. Astronomy is another big data example. It's rapidly growing, again, because of improvements in detectors and capabilities. The LSST, the Large Synoptic Survey Telescope, is going to produce about 30 terabytes of data each night. It'll start in 2022 or so. The Square Kilometer Array, this is an array of radio telescopes that will be located in Australia and South Africa. That's going to produce about 1.5 exabytes of data per year when it's completed sometime in probably the mid-2020s. So these are very large-scale data, and again, there'll be lots of scientists that want to look at this, that want to try to understand this data. Big data is also present in precision medicine. So what is precision medicine? That's where you take customized medical decisions based on individuals. So you understand as much as possible about that individual, and you compare it to what you know about medicine in general, and you come up with very specific guidance for that medicine. So one example, if we were, many of the cancers that arise are sometimes very specific, and the treatment varies significantly depending upon, say, the genetics of the person who has the cancer. If everybody who got cancer within a year, about 1.65 million people, would have their genome fully decoded, that would amount to about 4 exabytes of data, or about 400,000 times all the content in the Library of Science. A large amount of data. Another area that's increasing in the amount of data that they're producing is brain scanning. The technologies that are actually used, both for live brains and for dissected brains, is getting significantly faster and producing much higher resolution. So currently, a large 3D brain scan of a live person is about 100, 200 terabytes, somewhere in that region per person. If you take the newest technologies, when you look at a mouse brain, you dissect it and you scan it in high resolution, that would result in about 60 petabytes of data for one mouse brain. 3D scans of living human brains are producing somewhere around 4 terabytes of data, but there's easily a factor of 10 in improvements coming down the pike. And so a factor of 10 in resolution translates into a factor of 1,000, 10 times 10 times 10 to give you the volume. And so we're talking about data sets that per brain could exceed a petabyte. And if you want to do this over a large number of people to compare and contrast brains, you're then starting to talk about easily exabytes or beyond in terms of the amount of data. One good example of machinery in neurological science is shown at the brain-life.org site. That's a platform that allows brain scientists to share their data, their applications, and allows them to run those applications through a simple web interface. And it gives them access to a variety of resources. So this is, again, working toward that, trying to hide the details, make it simple for people to pursue their science. The image on the right shows 2 different methods that are used to map the white matter in the human brain. The white matter you can think of as sort of the cabling in your brain. It interconnects the gray matter, which is sort of like the computer site in your brain. And so it's very important to understand how those different computing locations in your brain interconnect with each other. And these are some of the methods that they're using to do that. One of the things that we need to do, I've hinted at it in all of these different science domains, is we need to understand how better to support big data science. How can we help scientists to do their tasks much more effectively? So I want to talk about 2 research projects that I'm involved with that are working on some aspects of the big data challenges that I've discussed. NSF has funded both of these. The first is OSIRIS. This is a multi-campus storage infrastructure that supports direct access to all the shared data between all of those sites. Another is SLATE. This is a system that would allow scientists to centrally define how they do their science and then dynamically allow that to run on a large and potentially variable set of resources across the country or across the world. So for OSIRIS, why OSIRIS? So the problem that we're trying to address here is storing, managing, and transforming and sharing all of this data is really costly. It's costly in terms of dollars. It's costly in terms of people time to create, support, and maintain the infrastructure. And it's costly in terms of scientists' time to try and deal with these higher level problems. So the solution that we're proposing is that we want to create an affordable, extensible, high-performance research storage cloud that has properties that you can't buy currently. It's built completely on open source software and very simple common off-the-shelf hardware that you can buy. So we're proposing to create OSIRIS. That's sort of an acronym standing for Open Storage Research Infrastructure. So our goals here are to make data access and sharing easy. One important point about this infrastructure, when we talk to scientists who have to deal with big data, the way some of them deal with it is copying a little piece over here to their computing cluster, processing on that, keeping track of all the data they produce, and then moving all the results back into this central storage location. That's very costly, it slows them down, and that bookkeeping is really problematic. So instead, we designed OSIRIS to allow those computing infrastructures, wherever they are on any OSIRIS campus, to directly access and compute on the data directly, writing results right back into the storage infrastructure. And the unique thing here is that we're trying to do this across multiple institutions. So you can have your colleagues at Michigan State or Wayne State working with you together on the same data at the same time with computers at each of those sites. There's some other features that come out of the fact that we're using something called Ceph. We can give science domains either block storage or object storage. Think of opening a web URL and getting content on your browser and maybe posting data back, or even just a file system view so that they can work with a common file system. Part of this is we're integrating tools that help do data discovery and let people use their institutional credentials. So we don't have to set up separate users and passwords to do this. You just use, for example, here at the University of Michigan, your unique name, and you log in, and then if the science domain has said you're a part of their science, you can get access to reading and writing that data. Another part of all of this is that we want to automate that network, that critical piece that interconnects the scientists with the data and the storage systems that are distributed with each other. So really, the main goal at a high level is really to enable scientists to collaboratively pursue their scientific goals without requiring significant infrastructure expertise. They don't have to become data storage specialists to be able to use this. This is an example of what an OSIRIS site looks like. We currently have 3 participating institutions in the project: Michigan State, University of Michigan, and Wayne State University. Indiana is also involved doing some of that software-defined networking piece. And so this is sort of a typical site. There's 4 high-level components. There's storage in the bottom left. There's virtualized services in the right. There's network measurement on the middle left, and data transfer, pardon me, on the middle left, and network measurement on the right. And so these characteristics are present at each of the sites, and they work together to provide a seamless whole at a top level. We currently have 5.2 petabytes in OSIRIS right now. That's over about 660 disks. The other project that I mentioned is SLATE. SLATE is an acronym standing for Services Layer at the Edge. This is a new NSF research project. We just started this in August. It equips the Science DMZ, and I'm going to stop for a second and tell you what a Science DMZ is. Many institutions have a firewall. You may have heard of it. It monitors and filters traffic from the general network outside of a campus, looking for people trying to do bad things or break into systems and blocking that traffic. One of the downsides of having these firewalls in place is that they get in the way of doing science. We need to move lots of information to and from many sites. And these firewall devices typically do bad things to our ability to move data. They significantly slow it down. So ESNet came up with the concept of a Science DMZ. That's where you have DMZ is demilitarized zone, where you put the interfaces to your science in a special area in your network that's outside of the firewall. And then you only allow certain services in there, but those services can perform at very high capability when talking across multiple campuses. So we're talking about creating some equipment that would sit in a Science DMZ and allow you to orchestrate resources at each of those sites to work together to make, for example, grids for science. It took Atlas hundreds of man-years to create their infrastructure. We want to try and take all that knowledge and automate the creation of this kind of infrastructure so that we can stand it up for any kind of science activity. So here's the SLATE concept. On the left, you have sort of an institution, could be the University of Michigan with different computing clusters. And then we put something called SLATE. We put some hardware and some software in the Science DMZ. And it can work together with these various computing resources that might exist at an institution and talk out to a SLATE central platform. And that central platform is run both by people operating the SLATE infrastructure, but also by science virtual organization managers. These are people who know the science for, say, physical ocean modeling. And they define that work centrally, and then it gets pushed out to all the campuses that want to support physical ocean modeling in a fairly transparent way. Another way to look at this, here's the SLATE platform. And again, the goal is to let these science users define what they have to do in one location. You have all the expertise there. You define it, And then there's a set of resource providers, people with storage, with networks, with computers that want to use those and make those resources available to do science. And we sit in the middle with Slate, and we match up resources that want to support science with science domains that want to do real work. And so ultimately, both sides win. It's much easier to deploy, to understand, and to manage. And that's what we're working toward here. So we live in an age of big data. It has a number of unique challenges and opportunities for science. Traditional methods of accessing, managing, and analyzing data are just not sufficient for this scale and complexity. The size, complexity, and richness of the data provides opportunities, though, where we can gain new insight and accelerate time to discovery. So these requirements for computing, storage, and networking are actually very similar amongst a lot of these domains that are hitting big data challenges. And the need here is to provide this machinery in ways that allow scientists to, as transparently as possible, focus on their science. So before I take any questions, I did want to acknowledge my colleagues who contributed to this presentation. Brian Arbor here at the University of Michigan and Chris Hill from MIT provided input in the movies for the ocean modeling. Ivo Dinov at Michigan provided details about the precision measurement work. Franco Pastilli at Indiana provided the details and information on neuroscience and brain science. And of course, my colleagues in Atlas, Open Science Grid, and the WLCG, who have helped put all of this infrastructure together. And last but not least, the Department of Energy and the National Science Foundation, who funded me and much of the work that I've actually presented here. So, thank you very much for your attention.